This looks a little bit different, doesn't it? So I'm on my computer this time. We're going to be recording my screen here because I want to walk through Excel, and we're going to talk about buffer capacity. By the way, if you have a MacBook, or sorry, if you have a Mac at all, if you hit Command Shift 5, it brings up an option you can record or capture your screen or record your screen. So just in case you didn't know that, Command Shift 5 is quite useful. I use it a lot. Okay, so we're going to talk about buffer capacity. And a buffer, right, is the resistance to the pH does not change if you add acid or base to it. It doesn't change very much. And the buffer capacity is how much it actually changes. It's the how well it resists a change in pH. We will see that, I think I mentioned this before, buffer capacity is at a maximum when the pH is equal to the pKa, right? So it's going to be the least amount of change when your pH is equal to the pKa. So we've gone through this whole equation of how to find pH of a buffer, right? You have the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of A minus over HA. I want to use Excel to solve this, and we're going to actually use Excel to solve this for a bunch of different starting scenarios, right? A bunch of different ratios of base to acid, right? And see how much add a set amount of, let's just say, base, and see how much the pH changes depending on the initial ratio. So I have a question off to the left, and we're going to just work through this whole question, or at least as much as we can. So buffer capacity measures how well a solution resists changes in pH when acid or base is added. The greater the buffer capacity, the smaller the pH change. We will use Excel to calculate the buffer capacity for a buffer system at different initial pH values. So consider a buffer that has a mixture of HA and A minus, and the dissociation constant of HA is 1 times 10 to the minus 4. If the Ka is 1 times 10 to the minus 4, we pick an easy number, right? Then the pKa is just equal to 4. So I'm going to put that in a cell here. The total moles of HA and A minus is 1. So right, that's the formal concentration. So using Excel, find 20 different relative quantities of HA and A minus that correspond to pH values roughly between 2.5 and 5.5. For each of the 20 buffer solutions, add 0.01 moles of NaOH and calculate the new pH after the addition. Plot the change in pH, that is delta pH, as a function of the initial pH of the buffer. By the way, we're basically going to be recreating figure 9.2, except I chose a different Ka value. All right. Well, let's just do one kind of like set of this equation here first, and then we'll do a bunch more, right? Then we'll figure out how to automate it. All right. So let's just say we have a situation where we have 50-50, right? Equal amounts of A minus and HA. So then if we wanted to find the ratio, you get to see all my keystrokes and all my mistakes now. Right, I know it's just one, but I want to actually put in a formula for this. And then I want to find what's the pH then of this solution. So equals, so remember pH is pKa plus log of base over acid. So pH is the pKa, so it's right there, plus log log 10 right? This is if you want to choose different base, like base E or base 2 or anything you want. We want log 10, so I'm just going to put log 10, and then the number would be right there, and the pH is 4, right? Which is what we expect, right? Because equal amounts of pH is equal to pKa. And then, so we can just kind of, let's do this for one problem and then we'll continue. Let's say we're going to add base to this, and we're going to add 0.01 moles. Oh, before I do that, I want to talk about this number. No, I want to talk about the new number. Sorry. We'll continue. Okay, so remember what happens if we add OH. A minus will increase, and HA will decrease. Right? We have basically the strong reaction. The HA plus OH goes entirely to A minus. Right? So the new A minus over HA would become, well, the old A minus plus OH, so the amount of base would increase. And if I want to find the new HA, it's going to be HA minus OH. And so it's slightly larger now. Since I plan on throwing this down through a bunch of different iterations, I'm going to put a dollar sign to make sure that it stays right there on that number. So now that's the new ratio. And we don't know anything about the concentration of OH that we're adding. Like, are we adding 10 milliliters, 50 milliliters? What volume of solution do we even initially have? Well, it doesn't actually matter because we're looking at a ratio here in NF, right? So if you had a ratio of concentrations, moles per liter would be the same as the ratio of moles because the liters would cancel out. So technically the volume is going up, and so the actual concentrations of HA and A minus would go down, but the ratio would be the same as talking about moles. So we don't care at all about that, which is kind of nice. Okay, so now we can find the new pH. The new pH is going to be equal to pKa plus log 10 of the new ratio. And so it only went from 4 to 4.017. That's pretty small. So the delta pH, right? The change in pH as a product of adding the OH. So it's going to be new pH minus pH. And there's the delta pH. Okay, I'm going to just move this down a little bit. And let's see what would happen if we had 0.9. And you know what? I'm actually going to replace this with I love to automate things, right? 1 minus B11. And then let's see if I can just drag this up. Oops, what's the problem here? Oh, I forgot to keep pKa. Whoops, see, the pKa moved up with it, and so I need to put a $sign on the 2 so that the pKa always stays in that cell.